Case study e-commerce website. This is the last lesson in this course. In this lesson, I am going to cover a case study on e-commerce website design. It's a simple case study, but it will cover a lot of topics that we have discussed so far in this course. So if you are asked in a system design interview to design a highly scalable e-commerce website, there are lots of pieces that go in this. So it's a website through which you could sell products, but behind the scene there are lots of pieces in this. For example, website design is one piece, maintaining the database is another piece, scalability, security, handling transactions. So there are lots of topics that go in this. Approaching the problem. So we will refer to the steps discussed in system design basics section, the lesson 2 of this course, and go over the 8 steps discussed in that lesson, and using that we will try to approach this problem. This interview generally lasts for around 45 minutes and you are expected to do it on a whiteboard. For this presentation, however, I'll be referring to this PPT only. One key point here is we have to distribute the time of the interview within a span of 45 to 60 minutes. So, we have to time the interview and we have to make sure that we don't give too much time to just one section so that the other sections are left out. So there are some key sections that should get more time. For example, low level design should get more time. Database design also should get some time, and requirement phase should get some time as well. Designing an e-commerce application. So what is expected from an e-commerce application? So first of all, this is a very broad question, and building an entire e-commerce application is certainly not possible within a span of an hour, right? So even the interviewer knows that, but we need to come to a feasible solution. So what all he is expecting from this problem. An e-commerce application allows customers to search for products listed on its website. So you can browse the products on its website, add them to a cart and shop them. Right? Finally, you can check out the shopping cart and buy the products. User can also rate the products, provide reviews, provide comments on the reviews. E-commerce stores have a lot running behind the scene apart from this. For example, they have something like recommendation engines, they store clickstream data, they have catalog management, inventory management. There is a lot running behind the scene, and coding this in entirety within a span of 1 hour is not possible. So step 1, when we approach this problem, the first step is requirement gathering, which is very important step. So if we make mistakes in this step, the entire approach we are following in the remaining steps would not be correct. So it's very important to ask the right set of questions in this step. What are the typical questions that we can ask in this step? So for example, user can visit the website, browse the products, add the products to the shopping cart and check out and buy the products. Is this the only piece expected from this particular interview question? If the interviewer says yes, that means your scope is decided here. So this particular step helps you in deciding the scope of the problem. Apart from this, you can ask questions like, do I need to include a recommendation engine in scope or not, or whether we are interested in maintaining product discovery like some sort of a search engine or not, or when the users have placed orders on the website, there is some sort of order history. Do we need to maintain order history in the database or not? Questions like that. This help you scope the problem. Based on the scope, you can come up with a set of requirements that you can write at the corner of a whiteboard. So for example, you can write functional requirements. So for this particular case study, I am thinking these 4 can be the functional requirements. User can view, search the products and discover them. User can view the product detail. User can add products to shopping cart. User can then check out the product and buy them. There can be other non-functional requirements also, like the system should be highly available. The system should be scalable to support different loads. For example, during a festival like Christmas, there can be tremendous load on the website and it should not go down. The system should scale to new set of users. Extended requirements can be analytics and creating an API for third-party users. Extending requirements come into picture only if you have time left during the interview. Step 2, back of envelope calculations. Before we go into this, let's confirm from the interviewer first whether they need this or not. Usually this is expected in a system design interview. Once you have confirmed this, we can do some back of envelope calculations. First, we make some assumptions and we ask the interviewer whether our assumptions are correct or not. So let's say total number of users on the website is 25 million users. Daily active users on the website is 5 million. Total number of products on the website is around 1 million. Number of images per product. So every product will have some sort of images like thumbnail images or product images basically. So we are saying on an average each product has around 3 images of 100 KB each. Total sales in a day is 1 million users buy daily. Size of metadata per product is around 500 bytes. So product has different kind of attributes, right? Product name, product description, and product images where they are stored, product price. So all these attributes might say comprise of around 500 bytes of data. This is a ballpark estimate. Size of metadata for users. Even the users logging into the application, they have attributes like username, their email, their credit card information, other details. So roughly I'm giving 200 bytes to this. Now let's do some calculations. So storage for the total users and products. So we said 25 million is total number of users and each user's metadata is around 200 bytes and plus 1 million into 500 bytes for the total number of product metadata. So this gives us roughly around 6 GB of data that we need for storage for users and products metadata. Now images, they consume more memory. So we will know how much storage space they require. So we said 3 images per product. We have 1 million products. So 1 million into 3 into 100 KB is roughly 300 GB. So we are giving some buffer over here. We increased it to 500 GB to take care of more pictures that are added later for new products. So based on this, we can calculate requests per second. We said 5 million active users in a day. So let's find out number of active users per second. So 5 million divided by 24 into 60 gives us around 58 requests per second. Using this, we can calculate the bandwidth per second. So 58 into 300 KB. We said 300 KB of data is being added into the system. Plus 500 bytes. This roughly comes to around 18 megabytes per second. Next step is service API design. Very important step. This contains the interface methods that we'll be using, and these methods get invoked by the UI, get invoked by the mobile app, and you can also give these methods to third-party users. So very important step, and I particularly usually use REST for describing these methods, but you can also use SOAP over here. You can also mention the technology that you can use. So I'm more comfortable with Java, but if you are comfortable with Python or Ruby on Rails, you can always mention that using that technology you can create the API. Let's cover some methods now for the service API. Let's start with search. So I'm expecting there is on the UI there is a text box where the user can type a contained search with some description about a product or a book. So if you are thinking of searching for a book like Thinking in Java, you just search for Thinking and Java, 2 words, and it might bring you results with all the books that contain this word in the product title. So search product is one method, API key and search query. Search query will contain the search text. API key is nothing but a key that is used to check out who is accessing your system, and based on this key you can throttle the users. This is usually this attribute is used in third-party APIs. Product detail is another important method where you can give a description of a product based on product ID, which is a unique ID given to each product. At the bottom of the screen you would see JSON response that can be returned if it is the response is coming in terms of JSON. This is a handy way you can show it on the screen to the users, to the interviewer, that a JSON response can be returned. Add product to cart. So shopping cart is a very important concept for e-commerce. So when a user is browsing the website, they can continue adding products to their shopping cart and later check out and buy them. So this each shopping cart that a user builds can be given a unique ID called cart ID, and in it you can add product ID and their quantity. So these are the attributes depicting this, and add product to cart is a method for adding a particular product to a shopping cart. Similar to this, there can be other methods like delete product from a cart, or update cart if you want to change quantities of a product that you're buying. Checkout cart. This is the final stage where the user payment information can be used, and the method can talk to a payment gateway, third party payment gateway, and deduct money from user's credit card or bank account, and finally create an order in the system. And from that point onwards, the order processing systems will take over, and they will extract this data and move the data into order fulfillment on all those systems. So these systems are out of scope for this. We confirmed this in the requirement phase only. Very important step next, database design. For the perspective of this simple e-commerce website design, I'm choosing MySQL database, relational database. For high scalability, NoSQL seems to be a better choice here. So I'll come to it why NoSQL is a better choice. Let's go to point number 2 for now. There are three main tables as far as this e-commerce website is concerned. First is the user table that contains user information. Then there is an orders table that can contain information for the orders users have placed on the website. Products table containing information about products. Now, if you use a NoSQL database, then the user table can contain the complete details about the user as well as the orders he has placed. So there can be a column that contains the entire order table in it. So when you pull the information for one user, you also pull all his historical orders at one shot. You don't need to include a join to another table to pull this information. For a website with tremendous load and huge number of users, this can be very useful, very fast from performance perspective. But for this website design, let's start with relational database. You can always mention this to the interviewer that I'm starting with a relational database for now, but scalability is an iterative process, and I will always come back to it later and redesign using a separate DB. But for now, you can concentrate on using a relational database. So this depicts a simple ER diagram for the e-commerce website. So as I mentioned, there are the important table is users, but here I am calling it customers. So customer table, order details table, products table, and category table. So these 5 tables are key. Category contains the category of the product. For example, whether it is books or toys or different categories, and using that you can figure out what kind of product it is. And then this order details table is a very important table. It contains the link between order ID and product ID. So it is a one-to-many relationship. One order ID can contain multiple product IDs, and then order table is linked to customer, so the customer who is placing the order. If you see, there are 2 more tables like shipment and shipment details. So these might not be needed for this particular interview, but if you have time, you can draw them. The main point here is I have not drawn all the tables in detail here. Only some key columns are mentioned over here, and the last 2, shipment and shipment details, can also be omitted if not needed. Let's go over the next piece, and this is the high level design of the system. The diagram here shows a typical entire architecture where there is a client load balancer that's invoking a web tire is invoking a business tire, and then business tire is finally sending request to a database layer. So at each layer we can have some specific code deployed and replicated for scalability. So this is a typical high level architecture that I'm proposing for this e-commerce website. So there can be multiple clients, so web client or mobile app for this, and there can be one or more load balancers. Even though the picture here is depicting one load balancer, but there can be multiple load balancers here. And Behind the scene, there can be different services deployed on application servers. Even though we are showing just three services here, there can be multiple services on multiple instances of application servers, and within these multiple services, these services might be replicated. So there can be multiple instances of search service that are running behind the scene. And then in the backend layer, we can have a cache, database, file storage for hosting the pictures of the products. Let's go more in depth on the low level design. From a low level design perspective, some of the key components for our e-commerce story are product search, product detail, adding to a shopping cart, and then the last three steps, displaying the order, checkout, order confirmation. Even though I've written over here, it depends on the time and on your interviewer whether he wants this information from you or not. If he expects you to cover these three too, then feel free to go in detail on these topics as well. But for the purpose of this presentation, I am only covering the first three topics. So low level design, first piece, search service. So how does the search service get invoked? So basically the user enters some text on a text box at the top of a website and searches for a product and hits a go button, and the request comes to your search service. And then the search service behind the scenes collects this request, creates a new request and sends to another layer, which can be a search server. For example, it can be a Lucene server, or it can be Solar server, or it can be an Elasticsearch server that runs on top of an index that it has built out of text data, and it can send you the response back with product IDs, matching product IDs to your search. And from those product IDs, you can further pull metadata directly either from cache or from database and return the result to the users. So search service is one instance of a service that is replicated across multiple instances and talking to a set of search servers. Indexing on the search server. So how does indexing on the search server work? Even though I have used Elasticsearch server here, I have mentioned for using that, but you can use Solar as well as you can use other. For very simplistic websites, you can directly fire a like query on a SQL database for this. So here is a typical diagram of how a search service would look like. So there can be multiple replicated instances of search service, and they can talk to multiple instances of Elasticsearch servers with a shared set of indexes that they have built. So how does the Elasticsearch build the index? You can feed it text data that can be extracted from your database for products like product description, product name, product price, etc., and just feed it to these Elasticsearch servers, and they will create indexes out of it and store it in some sort of database that is built inside these servers. And then most of these servers have REST API. You can create a search query and invoke the REST API of this search servers, and they will return the response to you. Low level design part 2, product service. So product service is nothing but a service that will return to you description about a product if you given a product ID, or it can contain other methods like add product. So that is out of scope, where vendors can add new products into your system. It is a simple service. You just pass a product ID to it from the UI, and it will extract the product detail directly from the database, or it will go to the cache. Here there is an important point that I would like to mention is lot of product information is static data, which is not changing frequently. In fact, other than price, I don't think there is other information that would change frequently for a product. So a lot of this information can actually reside in cache. So for frequently accessed products, you can follow the 80-20 rule. 80% of the time people would be spending on browsing 20% of the products. So you can just figure out those products based on maybe analytics data, and you can put those products metadata in a distributed cache. So directly for those particular products, you can pull the data directly from the cache. You're not hitting the database, and this way your product description queries will be very fast. So this is shown in the diagram here. So product service is again replicated, and this is mainly read-only data, and it can go to the cache first, and if the cache doesn't have the data, then you can go to the DB and pull the data from there. Last service that I'm going to cover here is shopping cart service. This is the most important service for this project. So this is basically for maintaining the shopping cart of the user, where the user can browse products and add products to a shopping cart. Now there are two ways by which shopping cart can be maintained here. One is storing the shopping cart in the database, or storing the shopping cart in a distributed cache like Gemfire or Hazelcast. I am leaning towards using a distributed cache over here. It's a good out of the box solution, so you can put a distributed cache in your architecture, and you can, distributed cache consists of replicated cache servers, and it would automatically take care of replicating data and maintaining cache consistency. If you need more details on this, you need to refer to the reference section for reading more about cache consistency in the distributed cache, and you can directly pull the data from here. If you are doing a very small website, however, and you do not have too many servers, just one or two servers, you can actually use HTTP session for this, and you can use session replication if one or two servers, but this is only for websites with low amount of load. For this particular case, where we have too many users and too much of load, distributed cache seems to be a better solution. So you can have shopping cart, multiple instances of shopping cart talking to a distributed cache. So you can create a shopping cart ID, unique shopping cart ID for each user, and store data against that shopping cart ID in a distributed cache, and pass it around using from the UI, using hidden variables or cookies. You can store this shopping cart ID, and using this you can pull the information, and finally the user can check out the order based on this shopping cart ID. Last step, scalability and other issues. One of the very key steps about this website is availability. So even if a website like Walmart or Macy's.com goes down by say 1 or 2 minutes on peak load days, there can be millions of dollars loss of revenue. So high availability is one of the key factors for this website. So how do we maintain high availability? One main way to maintain that is replicating our services across many different servers. So even if few servers go down, there are always few that are up and running. So maintaining across different servers is the main way. But then CAP theorem says that when you get high availability, when you get high partition, you have to give up something. So in this case, we are giving up consistency. As partitioning is also important for us, the site should be able to scale to the number of users that are accessing the website. But when we give up consistency, we can always take a modest form of consistency. For example, we can use eventual consistency. So even though some machines are updated, the other machines can be gradually updated. Maybe you can use the order of updating, so first machine is updated, then you can update the second and third and fourth and so on. There are steps to do it. You can read more about it in the reference section. Finally, concurrency. If suppose there is just one book left in a store and say 2 users are placing order on that, if we do not have proper locks in the database for this transaction, then there is a possibility both users might buy the same book at the same time. However, in your inventory you just have one book. To fix this problem, there are two approaches. One is pessimistic locking and the other one is optimistic locking. So in pessimistic locking, when one user is accessing a record of a book, you just lock it. So the other user won't be able to access that record at all. And for the whole transaction, that lock will be held. Whether the user buys or doesn't buy, as long as he closes his session, the lock would stay in place. The other approach is optimistic locking. Optimistic locking is at the time of purchase, you see whether the particular row is being accessed by the other user or not. And if it is in use, is the order in process or not, whether the user is placing the order or not. If it is he is just browsing, he has not yet placed the order, then you at that moment you can go and place the order for this user. So pessimistic locking has low performance because it locks the entire row. The other user is not able to access it at all. While in optimistic locking, both the users are able to access the data. It's only at the time of purchase you are checking whether that item is not already sold or not, and then you place the order. With this, we come to an end of this case study. I want to make a point over here is that this case study might not be, completely correct. So I am open to any suggestions on making changes to this case study. So if you have more feedback on this, or if you want me to make some changes to this, please reach out to me. Please give your feedback, and I would upgrade this. I would change this to make it better. Apart from this, these are some of the references that you can refer to. For example, there is a good talk on Amazon architecture in highscalability.com. Also, you can refer to the remaining two links on microsoft.com and the other one on Quora. Thank you.